All right, today we are going to tackle what quadratic functions look like as absolute value functions. So your two worlds are colliding. Okay, so let's just start by quickly remembering what happens when we've got a quadratic function. So our quadratic function is going to have x squared. And let's start with x squared plus x minus 6. So just as a review, we know that if we wanted to graph this, we would factor it, and we would factor to x, x minus 2 times x plus 3. And from here, we would be able to see that we've got x-intercepts at 2 and at negative 3. So I could go ahead and come over here and say, here's an x-intercept, and here's one at 2. And I know I've got a y-intercept down here at negative 6. And then if I graph this thing, it would probably look something like this. Wow, super symmetrical. Okay. And then we have a vertex that's probably a little bit lower. So you've got your vertex, your y-intercepts, your x-intercepts, and this bad boy is opening up because this is a positive function. Okay, so we are going to take the absolute value of this, which isn't too terribly tricky. So let me draw this a little bit nicer real quick. Okay, so what was our function? We were working with y equals x squared plus x minus 6. Now, if I go draw that, we just said, we know that this has x-intercepts at negative 3 and positive 2. It's got a y-intercept at negative 6. So it's going to make some sort of parabola like this, right? Okay, something pretty close to this. All right, so this time we're going to take the absolute value of it. All right, so when we do that, what do we always do when we don't know what to do? We make a table of values. So let's make our table of values. We've got x and y. When you choose your values for your x values, look at your graph and be smart with what you pick. Let's start at negative 4 because we know that negative 3 is important, so we want to pick just a little bit past that. Then we'll pick. So let's pick negative 4. Oh my goodness. Okay, let's pick negative 4. And then we'll pick negative 3, negative 2. A vertex looks like it's somewhere around negative 1, so we'll keep going. We'll pick 1, 2. Let's pick 1. We need to pick 2 because it's an x-intercept also. And then we'll pick 3 just, for an extra one. Okay, so when we go plug these in, we have to remember to take the absolute value. So I'm going to say negative 4 squared is 16, minus 4 is 12, minus 6 is 6. Easy enough. Negative 3 squared is 9 minus 3. Negative 3 squared is 9. 9 minus 3 is 6. Minus 6 is 0. That makes sense, so it's still an x-intercept. Negative 2. So I'm going to plug in my negative 2, and it's going to say negative 2 squared minus 2 minus 6, and it's the absolute value. So I've got 4 minus 2 is 2. 2 minus 6 is negative 4. What's the absolute value of negative 4? 4. Be careful on that. Same with negative 1. Negative 1 squared is 1. Minus 1 is 0. Minus 6 is negative 6. The absolute value of negative 6 is 6. Don't mess that up. 0 squared plus 0, 0 minus 6 is negative 6. Absolute value of negative 6 again, 6. 1 squared is 1 plus 1 is 2 minus 6 is negative 4. And the absolute value of negative 4 is 4. Good. 2 squared is 4, plus 2 is 6, minus 6 is 0. And 3 squared is 9, plus 3 is 12, minus 6 is 6. There's a lot of 6's happening. Okay, so we're going to plot these. And we're going to see what this function looks like. So -4, let's see, I'm going to plot this guy in red. All right, -4, 6. So, okay, pretty close to what we had before. -3, 0. Same place, our x-intercept. -2, 4. Ooh, all right. -1, 6. Okay. 0, 6. Here it is. 1, 4. I feel like we're playing bingo. 1, 4. 2, 0. Back on our x-intercept. And then 3, 6. Oh, man, I drew a good graph last time. Okay, so these arms, I like to call these arms, on the outsides totally match. They look just like our original function, well, our non-absolute value function. But this inside is doing something funny. And in fact, what it's done, and notice I'm drawing a U shape at the top, is it's taken the bottom half of our parabola and it has flipped it upside down, right? Look, all the points are mirrored. Like, here's my y-intercept in purple, and here's the positive version of it. Because what's the absolute value of -6? 6. And like right here, at -2, at -4, what's the absolute value of -4? 4, right? So like if you look at this point, -4, its absolute value is 4. Right here, the absolute value of -4, 4. They all have the absolute value. So what we've done is take the negative pieces and the absolute value of them created the positive piece. So we've got kind of 3 sections of this. We've got these kind of arm pieces on the side where the absolute value is the same as the non-absolute value. And that's happening here. But in the center, we flipped this guy upside down because the absolute value is positive. All right, so if we keep that in mind, we don't have to do a table of values the whole time. We know the x-axis, or I'm sorry, the x-intercepts don't change. We know the positive areas stay the same. It's just this negative area that we needed to flip. So we can be smart about this and be a little bit more efficient. Let's look at another one real quick. Let's get another graph because, really, I need all the help I can get. Okay, what about this thing? What if we say y equals the absolute value of x squared minus 9. Okay, this is a quadratic function. It's difference of squares. So if I was going to factor this, if I just wanted to look at this without my absolute value bars, I would factor this to x plus 3 times x minus 3. So I know that my x-intercepts are at 3 and at -3, right? So I can come over here and here's my x-intercepts, okay? I know I would have, in theory, a y-intercept down here at -9. And so my parabola without absolute value bars would look like this. Now, once I take the absolute value, this whole negative area is going to get flipped and become positive because the absolute value of all of these y values have to be negative. So this -9 has to become +9. So when I take the absolute value of this, I'm going to leave all my positive values alone. and I'm going to flip all my negative values upside down. And then the blue graph is what the absolute value looks like. Okay, isn't that much more efficient than making a table of values? Now, like any good quadratic, we can turn this thing upside down. So, what happens in quadratics if we put a negative in front of our x squared? What does that automatically do? What does negative x squared look like? It turns your whole parabola upside down. The exact same thing is going to happen in absolute value. So absolute value of x, we learned in our last lesson, is a v that opens up. So the absolute value, the negative absolute value, if the negative is outside, that means that it's going to open down. Just like we've learned in quadratics, that negative flips everything upside down. So that's going to apply here as well. We're going to take this and combine it with this. So we're going to have an upside down parabola. So let's see what that looks like. What if we take y equals the negative absolute value of x squared plus 6x plus 8. All right, let's ignore our absolute value for just a minute. And I'm going to keep my negative outside. X squared plus 6x plus 8. How do I factor that? I would factor this to a negative x plus 2 times x plus 4. So where are my x-intercepts in this? My x-intercepts, I can't write, are at negative 2 and negative 4. So what does that mean for my absolute value? Well, remember, we saw that the absolute value doesn't impact your x-intercepts. So my x-intercepts are going to be at negative 2 and negative 4. That's not going to change. And if I were to graph this without my absolute value bars, my x-intercepts are here. I know it's opening down. My y-intercept, if I distributed this negative, my y-intercept would be down here at negative 8. So I know, let me make that red. So I know that my graph would look like this without absolute value bars. Therefore, this time, what's going to flip? The whole thing has to be upside down. So this time, the positive piece, this little guy, is going to do the actual flipping because it's negative. So this time, these pieces stay the same, and this is going to drop down when I take the absolute value of it. That negative flips the whole thing upside down, so it's completely reversed. Does that make sense? I hope that makes sense. It's like saying that the absolute value of negative 8 is 8, and then we multiply that by negative 1, and 8 times the negative is negative 8. So just think of this negative sign as being a straight up reflection. It flips the whole graph completely upside down. Let's do one more negative. What if we have the absolute value of x squared minus 4? All right, this time, if I ignore this, I would have negative x squared minus 4, negative x plus 2 times x minus 2. So where are my x-intercepts? My x-intercepts are at 2 and negative 2. So they're here and here. And without that, my function does this, right? But because it's absolute value, I'm going to take this whole positive part, because it's negative, and I'm going to drop it below and keep my original negative part. Does that help clear things up? So this red piece doesn't really exist. I'm just kind of using that as a helper to help me figure things out and be a little quicker about it, right? But it's not actually part of the graph. The final graph is just this kind of bottom piece, okay? And all I've done is take a portion, the middle portion of my parabola, and flip it over to go with its arms. That's it. I hope that makes sense. And remember, when all else fails, make yourself a table of values, and you can always check your work in Desmos. If you're not sure, put it in Desmos and see what you're getting and work backwards from there, okay? All right, good luck.